In this third video on nuclear and atomic physics, we will look at the half-life of the radioactive elements as well as many more practices that we haven't covered in the other videos. So half-life in radioactivity is an interval of time required for 1/2 of the atomic nuclei of radioactive sample to decay. And it can decay by change it spontaneously into other nuclear species or by emitting particles and energy. For instance, in this picture that you see, they show that amount of carbon accumulated during lifetime in a plant or an animal, it will take 5,730 years after the death of the plant or an animal to have half of the amount of this carbon in it. And in another 5,730 years, or a total of 11,460 years, another half of the carbon radioactivity to be gone and be half of the previous one. So from the graph below, from the table below, you see that carbon-14 has 5,730 years for half-life, and then potassium-40 is 1.3 billion years, and then uranium-238 has 4.5 billion years, just as much as Earth is. So right now we would have on Earth only 1/2 of the uranium radioactive elements left compared to when Earth was first made. Here in this picture, you see that in 4.5 billion years, uranium goes many different transitions, and at the end, you have the last element that will the half-life, which is polonium, and after the polonium you have lead, and that's where the transitions or radioactivity is gonna stop, and then each one of those elements has different half-life time. So if I have to calculate my half-life calculations, use a formula for the half-life calculations, I'm gonna use this formula where N is the number of elements left and sub-zero is the number of radioactive elements to start with. E is Euler's constant, it's 2.71828. So it's a constant, and then lambda is the decay constant, and then T is the time since the moment that the decay started. So time will be the solution for our problems. We will calculate the time it takes for half-life to occur. So let's look at some of the problems related to half-life. So if 100 milligram of neptunium-239 decays to 73.36 milligram after 24 hours, find the decay rate or the value of lambda in the growth decay formula for T expressed in days. So in the formula, again, I have the number of radioactive elements that we're going to end up with is equal to the initial number of radioactive elements times the Euler's constant to the power of negative lambda times the time. And so the number that I'm gonna end up with after 24 hours is 73.36 milligram. So it is 73.36, and to convert milligrams to kilograms, I have to times it by -6 instead of -3. And on the other side, I have the number I start with, 100 milligrams. So again, I have to convert milli into kilograms. That's again 10 to the -6. Then I have e to the power of negative lambda, and times the time is asked to be expressed in days. So I'm gonna just times 1 for the days. Then because there is one term on the left side and one term on the right side, and each one of them have 10 to the -6, I can cancel that part. So I'm gonna have 73.36 equals to 100 e to the power negative lambda. Then if I divide both sides by 100, I will get 0.7336 is equal to e to the power of negative lambda, And every time I have equations with the Euler's formula, I have to make my E on its own and then take the natural log of both sides. And then when you take the natural logs of both sides, the power of E jumps in front, so you would have negative lambda. Then you would have natural log of E. And what's interesting, and that's why we're doing this, natural log of E is equal to 1. So that term can be cancelled. And then on the other side, if I take the natural log of 0.7336, I get negative 0.3098. And now from here, if we cancel negatives from both sides, the same as multiply by negative 1, I get lambda is equal to 0.3098, or it is almost 31%. Then what the decay constant lambda actually means is the probability of decay per unit time. So that means 31% of the original value is going to be decayed in 1 day. In the next question, they say that carbon-14 is used for archeological dating, has a half-life, as we mentioned earlier, 5,750 years. Find the decay rate lambda for carbon-14. Again, I'm gonna start with the number left at the end. So this is gonna be the number left at the end equals to the initial number, and then I have e to the power of negative lambda times t. So in here I have 1/2 of the initial number be left, and then I have the initial number e, and then lambda, the one that I'm looking for, and the time is right here. I'm gonna plug in years, which is 5730. So my answer is gonna be per year. So lambda is gonna be how many will be decayed per year. So now if I cancel lambda n sub 0, because that's the amount of element that we're going to start with, then I have 1/2 is equal to e to the power of negative lambda times 5730. And then as before, I'm going to take the natural log of both sides, so I can move my exponent in front, and the natural log of e will become a 1. So I'm going to have the natural log of 1/2, which is negative 0.693, and equals to natural log of e is going to be gone, so that is 1, and I'm going to have negative lambda times 5,730, and instead of the natural log of e, I'm just going to have a 1. So now if I cancel my negatives from both sides, I'll get that the lambda is equal to 0.00021, or in other words, it will be 0.0121% per year. So this is how much of carbon will decay each year, because we calculated our time, we plug in the time in years. For the next question, they say cobalt-57 has a half-life of 272 days. If a sample has an initial mass of 2.24 gram and undergoes decay until it has a mass of 0.14 grams, how many half-lives passed? So as before, I'm going to start with half-life formula. So the number of the radioactive elements after some time is equal to the initial number of half of the radioactive elements times, so initial number times e to the power of negative lambda times t. And again, lambda is the decay constant and t is the time, and we can plug in the numbers in seconds or years or days, but lambda then will become the percentage of the decayed material that material has decayed over that time that we plug in, days or years or whatever that is, or per day or per year or per second, it depending. So here I have, at first I'm going to figure out what lambda is equal to. So because they don't give me the decay constant, so I need to figure this number out. And for that, I'm going to give the information that is given about half-life. So I will have half of the initial number of the radioactive elements. If I have, so lambda is not given, that's the one that I'm looking for. And then the time is 272 days for half-life. So I've multiplied by 272. And again, I can cancel n sub 0, the number initial, take the log of both sides. So I'm going to have the natural log of the left side, and then I'm going to have the negative lambda times 272. And then I'm going to have the natural log of e, which is 1. So that number is just 1. I don't have to copy it again. And that gives me lambda is equal to 0.00275. And we plug in time is days. So that's per day. So what that means is 0.275% of the radioactive decay element is going to be decayed per day. So then, since we know what lambda is equal to, so we figure out what lambda, the decay constant, is equal to, I can now figure out how many decays has passed. So in the next part, I'm gonna say that the number that is left is 0.14 gram, and I'm gonna plug in everything in grams, so I don't have to convert to kilograms, because on both sides are gonna be grams. And then I have 224 grams, the initial number I start with, and then I have e to the power of negative lambda. I just figure out 0.00275 and times the time. And this is the time that will show me how much time passed for me to go from 224 gram to 0.14 gram. So again, I'm going to divide by 224 both sides, and then take the natural logarithm of both sides. So this is what I have so far. And then after this, if I solve for t, so if I do my calculations for t, the t is going to be the time that has passed for the carbon 14 to go from 2.24 gram to 0.14 gram. The time would take is 1008.28 days. So if I want to know how many decays have passed, I have to divide this number by how many days takes to half time the amount, so that would be 272. And this will give me that the number of decays is equal to 3.7, or approximately 4 decays. In this question, they say after 64 days, the activity of radioactive nuclide has fallen to 1/16 of its original value. Calculate the half-life of radioactive nuclide. And at first, I'm going to have to find what the decay constant is. So I'm going to have 1/16 is left of the original number, and this will be the original number. So on the left side I have how much left, on the right side I have the original number, then I have e to the power of negative lambda times t. They say 64 days, so that's going to be my t. N sub 0 can be cancelled, and then I have the natural log of 1/16 is equal to negative lambda t, and I have the natural log of e. And instead of having T, I'm gonna plug in 64 days. So again, my T is in days, so my result is gonna be per day. So this one is 64. The result for lambda is gonna be percent per day. So after this, I have lambda is equal to, I will have the natural log of 1/16, and all of that divided by 64. That is equal to 0.0433, or 4.33% per day. So that's how much radioactive element decays. 4.33% of it is gone within, or decayed within 1 day. And then the next one, I have to calculate half life. So right now I'm gonna have 1/2 of the life, so initial value. So on the left side I have initial value, or the leftover value, which is 1/2 in our case because they ask for half-life. And then I have the initial value on the right side, and then e to the power of negative lambda times t. And then again, in this case, I'm calculating the half-life time because I'm plugging in the resultant is going to be 1/2 of the initial value. So to do that, I can again cancel initial value, take the natural log of both sides. So I'm going to have natural log of 1/2. On the other side, when I take the natural log of e, the values of negative lambda and t jump in front, and then I will have the natural log of e, which is 1. And then I can plug in the lambda value that I found. So this is the lambda value that I can plug it in. So I have the natural log of 1/2 is equal to 0.0433 times t, and this is the half-life. So this t is the half-life t. So the half-life t, the time it takes for the element to decay to 1/2 of its original value. So I get 1/2 life is equal to 16 days. In this video, I want to go back and revisit some previous beta and gamma reactions that we mentioned in the previous video. So I want to do a few more questions related to it. And here in this question, they say, in a possible fission of uranium-235 by a neutron, 2 large fragments, one of which is Xeon-140, are produced along with 2 neutrons and considerable energy is released. What's the atomic number and mass number of the other fragment? So in this question, we have 1 neutron. Just to mention that if you have a proton, you have 1 nucleon in the nucleus. So it's only 1 proton, because nucleons means neutrons and protons together. So this is the amount of how many of them together. This is the amount of how many protons you have. If you have neutron, that means you have 1 nucleon in the nucleus, but you have 0 protons. And then if you have an electron, that means you have 0 nucleons, because electron is not in the nucleus, and then a -1. So that's how you represent each one of them. So in this case, we have a neutron that is bombarded into uranium-235. So I have plus uranium-235 that has 92 protons. And what is the number of neutrons? Try to answer it and maybe pause it. So if you pause it and you figured it out, so the number of neutrons would be 143. It's the difference between 235 and 92. 92 tells you the number of the protons. After this reaction, you will have Zion, which is Xe140. It has 140 nucleons and 54 of them protons. Then you have an element that you do not know what it is. So there's some element that you have no clue what it is, and it has the mass number and the atomic number that we have to be figuring out. And then you also have that they say 2 neutrons in this reaction. So you would have 2 neutrons, so there would be 2 neutrons with 1 nucleon and 0 protons, and the energy released, so in plus some energy. So when we look at the equality of this equation, on both sides we have the same amount, we need to have the same amount of the protons. So I have 0 plus 92 is equal to 54 plus this atomic number for the element that I do not know. So from here I have this element, the new element, would have 38 protons. You also have to have the same amount of nucleons on both sides. So on the left side you have 236 nucleons, and on the right side you have 140, then you have A, and then you have 2 neutrons. So on the other side you have 140 plus A and plus 2 neutrons. So from here I can see that A is equal to 94. The new equation for this reaction would look like, so the element with the atomic number of 38 is strontium, so it looks like it might be an isotope of strontium. For the next question, they ask you to write the equation for the process by which a radioactive radium isotope, radium-226, emits an alpha particle and becomes a radon isotope, radon-222. What they're saying is you have radium, and after radium emits the alpha particle, you have radon and the alpha particle. And the alpha particle is the helium, that is a helium ion. Ion means missing electrons. So you could rewrite this equation as well as, so instead of the alpha particle, sometimes in the equation you can see as helium with a 2 plus. That means it's a positively charged ion, the one that is missing 2 electrons, so it has a positive charge of 2 protons. And it has 4 nucleons, which means it has 2 protons and 2 neutrons. For the next question, they say write the equation for the decay of the radioactive lead isotope plutonium-209 into the bismuth isotope bismuth-209 by the emission of the beta particle and an antineutrino. So when they say you are emitting a beta particle, that means you have a beta negative decay, and the total number of the protons before and after, so the total number of the protons before and after has to be the same. So one of the neutrons will become a proton, and the element becomes not lead anymore, it becomes bismuth with the atomic number 83. So the sum of the protons on both left and right side must match together, so 82. In this question, they say write the nuclear equation for the transmutation of a radioactive uranium isotope 234 into thorium isotope thorium-230 by emitting an alpha particle. So again, when you write the alpha particle emission, you have number of the proton must match number of the protons on the left and right side. So the sum of them has to be equal to 92. And instead of alpha particle, you can rewrite helium 4 with by showing that it is helium ion. Could write this equation either way, and again always check for the number of the protons matching the number of the protons on both sides. If you choose to write alpha particle as helium, then make sure you include 2 plus on the right top side of the helium to show that it is an ion that is missing 2 electrons, and its charge is the 2 positive charges of the protons. In this question, they say a proton collides with a new nitrogen isotope, nitrogen 15, forming a new isotope and an alpha particle. What is the isotope, and write the nuclear equation. On the left side, I have a proton and the isotope of the nitrogen, and on the right side, I have a new isotope and an alpha particle. So the sum of the protons on the left and the right side must match each other. So that means the new element that I do not know, that's why I call it X, has the atomic number that has to add together to 8 as the way it is on the left side. So atomic number here must be a 6. And then I still have the alpha particle, and I have the left equation, and the number of the nucleons on the left and the right side has to match as well. So that means the nucleon number or atomic number, or the mass number on the right side has to be equal to 16 as well. So that is 12. So from this information, you don't have to do this, but just if you look at in the periodic table, you will see that this element is carbon, because carbon has nucleon number 12. So mass number is 12. So I have only like 2 minutes left to finish this video. I'm gonna stop here. This was our video 3 on nuclear and atomic physics, and mostly on half-life and some radioactive reaction. And the next video, I have to make one more. So the next one was probably going to be our final video, and in that video we're going to cover more practice questions on nuclear physics. And thank you for watching, and I'll see you in the next video.